All right, welcome back to Easy Math with Nick. Long time no see, right? Today we are on video number 19, and today we will be doing a non-calculator free response question, number 4 specifically, from the AP Calculus 2025 exam, specifically the AB exam, um, which I'm pretty sure the BC guys have different, 4 different questions than the AB guys, so although their calculator questions I think are the same, so. Um, anyways, that's not grammatically correct. But anyway, let's begin. So today this question's rather short, so let's speed through it as fast as we can. Just joking. We're gonna take our time, but wow, almost forgot how to record a video. I'm speaking way too much in the intro. Okay. The continuous function f is defined on a closed interval -6, from -6 to 12. The graph of f, consisting of 2 semicircles, nice, and 1 line segment, is shown on the figure. And they tell us let g be the function defined by g of x equals integral from 6 to x of f of t dt, time differential. Okay, find g prime of 8. Give a reason for your answer. Okay, well, you need to give a reason. So they tell you, well, let's label this part A. G of x equals the integral from 6 to x of f of t dt. Not f of x. You can't have the same variable in your integral as what's up here. You can't say f of x dt and have an x up there. No. That's confusing. So that's why they didn't do that, right? If you remember, calc teacher probably told you that. Regardless, if we want to find g prime of 8, what is g prime of x going to get us? Well, by the fundamental theory of theorem of calculus, which is, I assume, the reason that they want here, g prime of x is going to be equal to f of x. Because, well, if we were to, I'm not going to prove the fundamental theorem of calculus, but that's going to be f of x. You know what? I'll give a reason. So if we were actually to evaluate that integral, what this would look like would be the antiderivative f of capital F of x minus that, right? The antiderivative evaluated at x minus the antiderivative evaluated at 6, right? That's also, I think, the second part of the fundamental theorem of calculus, if I recall correctly. So now, if we take the derivative of, well, we got our both sides here, right? If we take the derivative with respect to x of both sides, we'll get g prime of x equals, what's the derivative of an antiderivative? Well, the original function, right? That's the whole point. That's the whole definition of what an antiderivative is. So we'll have equals f of x, and what's the derivative of the antiderivative at 6? Well, this is just a constant, right? It's just a number. That's not a variable at all, so that's just 0. So that should be obvious, but that's why this holds. So that's not our answer, though. You wouldn't circle your answer anyway. But if we want to find g prime of 8, it's just equal to functional value of f at 8, which is 1 right here, right? So that's our answer, 1. I'm circling it, but on the AP exam, don't circle it because your work is part of your answer, because you need, 1, a reason, which you would state fundamental theorem of calculus. And what is, well, your work? Your work is part of why you get points, so you don't just circle your answer. Although you probably do that on your teacher's tests. For the AP exam, I wouldn't recommend doing that. Okay, part B. Find all values of x in the open interval that we mentioned before, at which the graph of g has a point of inflection. Okay, so how do we define a point of inflection? Well, in order to determine what could get us a point of inflection, we would look at g 2 primes of x and set that equal to 0. That just gives us values for x that satisfy this, gives us potential values of x at which a point of inflection could occur. So this is just giving us our candidates, right? It doesn't mean at all of these x values at which g double primes of x equals 0. That doesn't mean for all these x values, at each one of these x values, there's a point of inflection. No, that could be the case, but not necessarily so. So let's look at, let's first find g 2 primes, right? So we said g prime of x equals f of x. So g 2 primes of x. Second derivative of g would be first derivative of f. Okay, you could kind of see where I got that, right? Power saving mode. Get away. Okay. So if we want to find g double prime, where g double prime of x is equal to 0, we got to look at where the slope on the graph is equal to 0. So essentially, where the derivative of the graph of f is equal to 0, the slope, right? I wasn't wrong in saying that. But that's going to be when we have a horizontal tangent, right? Yes, but there's also another little asterisk here. Asterisk, or when g double prime, the second derivative of g, does not exist. So that's a little how do I put it? An asterisk, another thing we have to watch out for here, because we can still have a point of inflection even at a point where the second derivative doesn't exist. So we still consider that to be what we would traditionally call a critical point. Because we're not dealing with a function here, we're dealing with this graph. It's easy to see which points here second derivative of g won't exist, or in other words, where the slope is where the derivative of f doesn't exist by just looking at this graph. But let's just take a look now. So for our first contender, I think it's easy to say that negative x equals -3 will grant -3 comma -3 is a potential point of inflection, because there's a horizontal tangent, because it's a semicircle, right? We can see the tangent line would be something like that. And that goes the same for 3 comma 3 as well. Those are very likely candidates for points of inflection. Well, let's also look at where the second derivative of g, or the first derivative of f, well, does not exist. If we look here, we have a vertical tangent, right? Wow. Okay. That indicates to us that the derivative of f at 0 does not exist. So g double primes of x does not exist. So this could be a point of inflection right here. Could be. We'll test in a minute. But let me erase what we had over here, so not to confuse you. And finally, our last point here, which the slope either doesn't exist or is equal to 0, is here. Because they're sort of, we would get two different derivatives by approaching from the left and the right. We would get approaching what? Negative infinity from the left, which is interesting to say the least. But we would have approaching, and then we would have what? A slope of positive 2 from, 1/2 from the right. So, yeah, those are not equal. So, the first derivative of f does not exist at that point, which would mean, I'm not going to repeat myself again, but I will. The second derivative of g also doesn't exist there. So let's test all these points for, let's test all these potential points for potential spots for points of inflection. If we look, the definition of a point of inflection is where, if we do a number line analysis, that's the official way to do this, of g double primes, and we look at this point, let's test -3. Beyond -3, the second derivative should be, the sign of the second derivative should change between -3 and before -3 and after -3. If we look before -3, the second derivative, or the slope of the graph of f, is negative. So we're negative before, for values smaller than x equals -3. For values greater than x equals -3, the slope is positive, because look, I'm sure you can see that, but that's an example right there where we would have a tangent line with a negative slope, and up here we would have a tangent line with a positive slope. So we're going from negative to positive there, and that's occurring at this point where the derivative is equal to 0, because that's the very bottom of that semicircle, where if you drew the tangent line, it would be fully horizontal, as mentioned before. So we're going from negative to positive. So -3 comma -3 is one of our points of inflection. So we can write that down and save it there. Now let's test 0 comma 0. So if we do this again, do another number line. Not going to bother erasing the same one. If we look before x equals 0, we're sort of approaching, tangent lines approaching vertical, which the slope is approaching vertical. The slope's approaching positive at infinity. So or positive before 0. And after 0, it's sort of also positive, right? If we look here, right, a little bit past 0, we also still have a positive slope. The slope of the tangent line to points immediately after 0 is still positive. So there is no change in the sign of the second derivative. So 0, 0 is not a point of inflection. Next, let's test. Well, I don't think we need to test 3, 3 because it's the same story as the other when we were dealing with the other semicircle, right? Except this time, the second derivative is changing. Well, the second derivative g, or the first derivative of f, which is the intuitive way to look at it, is going from a positive to negative. So positive before x equals 3 to negative after x equals 3, because that's before x equals 3, and as you can see, that line has a positive slope, the tangent line has a positive slope, and after, it's going to have like a negative slope. So, not like a negative slope, it will have a negative slope. And that's just sort of the inverse that we saw here with the other semicircle. But that should make sense intuitively. You might even just glean that just from looking at the graph without me drawing the little tangent lines on there to help you visualize that. So that is definitely a point of inflection. Now, finally, let's look at 6, 0, 0.60. Now we have a slope from the left, the derivative from the left at x equals 6, approaching negative infinity. So that's definitely negative, and it's much easier to see that the slope of the line, a linear graph after x equals 6, is positive, right? You don't even need to draw tangent lines because it's just a linear function. So 6, 0 is also a point of inflection because the sign of the second derivative changes before and after x equals 6. So these 3 will be our points of inflection for part B. And hopefully that was self-explanatory. I tried to do a little visual representation to show how we're changing from tangent lines with negative slopes to those with positive, to show that we meet the criteria for a point of inflection. So just to repeat, if you weren't aware, a point of inflection first has to meet the criterion that it occurs at a point where the second derivative is equal to 0, or the second derivative does not exist. It could be either or. And once we find the x values for the critical values, if you will, for which that criteria are met, then we check to see if the second derivative changes signs before and after that point of that potential point of inflection. So to determine if it is actually a point of inflection. So there you go. You probably knew that already, but I like to be as thorough as I could in these videos. So now they're asking us to find g of 12 and g of 0. Okay, how elementary. How elementary. I think I'm on to, what am I on to, right? What am I saying? So, okay, trying to seem snobby. It's not very, whatever, I don't know. Okay, what was I going to say? Trying to use big words. That's what I meant to say. How elementary. So, sound like I'm so full of myself. Gotta take it down a notch. Okay, if we want to find g of 12, they give us the function for the function for g. If I'll write that first. G of x equals the integral from 6 to x. That's a funny integral. Of f of t dt. So the area under the graph of f, well, not the area, but the integral. I could say area if this wasn't under the x-axis, but whatever. I'm sure someone would have corrected me if I picked it up. So g of 12 would be the integral from 6 to 12 of f, which, if we look at our graph, that is, we can erase these circles now. The little dots, not circles. That will be this triangle we have here. So we just need to find the area of that triangle, which is 1/2 base of that triangle, which goes from 6 to 12, so that's 6 times height. What's the height of that triangle? 3. Fantastic. So that's 1/2 6 times 3. That's 9. Bang. There you go. That was easy. I'm only circling my answer so you can see it easier. Now they want, g of 0. Isn't that interesting? Our lower limit is greater than our upper limit. Oh no, that's not good. Well, if you know your properties of integrals, you'll know that this equals the integral from 0 to 6 of f of t dt. Because you can, with the property of integrals, you can swap your limits, and that just adds a negative sign out front. So that's pretty nifty for us here. And now we're concerned with, instead of that area, we're concerned with this area under this semicircle from 0 to 6. So we're finding half of a circle, half of the area of a circle. So it's going to be 1/2 pi r squared. And what is our radius? We have a radius of 3. That's going to be this here. That's our radius. You can also think of it as that. You know what a radius is. I don't have to tell you. 1/2 3 squared, which equals 9/2 pi, 9 pi over 2, whatever. So that is our functional value for g at 0. So that wasn't so bad, right? All right, let's move on to part D. I told you this would be a quicker video. I'm making it longer than it has to be. Find the value of x at which g attains an absolute minimum on the closed interval -6 to 12. Justify your answer. Have to justify. How annoying, right? Nah, it's not that bad. Let me tell you right now. Okay. So we want to find when g has an absolute minimum. So what we should be doing here is setting g prime of x equal to 0. We established that g prime of x is equal to f of x. So essentially, we want to be finding the points for which f of x is equal to 0. So what are the x-intercepts, or what are the roots of f? At what points does f cross the x-axis? So stroke eraser. Okay. Well, I could tell you right here, and right here. Okay, so we have 3 points already. So x equals -6, x equals 0, and x equals 6. That wasn't so bad, right? We just find where the graph touches 0. That was easy. Well, now we need to test all these values to see where we get absolute minimum. Before anybody corrects me, there's something else I didn't do here. We are trying to find an absolute minimum on a closed interval, which means we also have to test the endpoints of the interval. So let's do that first before we even begin, because this is the most easily missed step. So for x equals negative, well, it just so happens that one of the times we cross 0 is also at an endpoint. So that's funny. So we'll test x equals -6 first, which will be the integral from 6 to -6 of f of t dt. Which, that isn't that bad, because once again, if you recall, we can swap our limit. Now, stick with me here. What is the integral from -6 to 6? So if I erase our little circles, or little dots once again, it's going to be this area added to this area, right? Because we're going from -6 to 6. Now, these are two semicircles which have the same area, but one's under the x-axis, one's over the x-axis. So the integral from -6 to 6 is going to be 0 because these areas cancel out. So that gets us a nice small value of 0. There you go. Nice. Oh, that turned out nice, right? Now let's check the other endpoint, 12. Ooh, scary. Now hopefully I have a feeling this will turn out nice because I feel like we did this before. Didn't we find g of 12 before? It was equal to 9. So I don't have to do my work again. If you want to, you can, but I'm not going to. It was just that triangle on the right there. So hopefully you can find the area of a triangle. If not, good luck. There you go. We tested our endpoints. So now let's test all of the values, these two values here, which we didn't get to yet. So if we find g of 0, That's going to equal the integral from 6 to 0. F of t dt. Once again, we can swap our limits, 0 to 6, f of t dt. And what is that? 0 to 6. That is this semicircle here. But we make the area negative, so it's going to be 1/2 pi 3 squared. So it's going to be negative 1/2. So there you go. Because it's 1/2 pi r squared. So it's 1/2 pi times 3 squared. 1/2 pi times 9. There you go. So that is g of 0. I think that's going to be our smallest value, but let's finally test g of 6 equals the integral from 6 to 6. Okay. Ooh. Of f of t dt. And that, of course, is equal to 0, right? Because we're integrating a tiny sliver. You get that. That's a fundamental integral rule. So if we look at all of our points at which we just found the functional value of g4, 9 was the largest, but they're asking for an absolute minimum. So 9 is out, so we could just cross out 9. 0 is also out because we got 0 twice, and it's not the smallest, which is negative 9 pi over 2. So that is the value at which g will attain an absolute minimum on that closed interval, because we tested the endpoints and we tested all the points at which g prime of x was equal to 0, which is f of x. So that is when g will obtain a minimum, an absolute minimum. So there you go. That was this fourth non-calculator free response question from the AP Calculus 2025, AP Calculus AB 2025 exam. Thank you for sticking with me. Trying not to get too off track there with my deranged comments to myself. It's hard to keep yourself from going insane sometimes when making these videos. It's probably why I took a big break from making them, but I enjoy doing it. And I'll keep everybody posted with another video very soon. Big video, number 20. It'll be very special for me for sure. So looking forward to that in the near future. Thank you for sticking by. This was Easy Math with Nick, video 19. On points of inflection and absolute minimum for that part D. Thank you.